Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello, dear students. My name is Teacher Jean-Marie, and I want you to get ready to continue with me physics of Senior 4. Students, I hope you remember that we have physics, and in all of this time of 30 minutes. So students, you remember the unit that we are discussing in is work, energy, and power. This is unit number 4. And the lesson that we are going to see is the work done in deforming materials and strain. This is lesson number 4. So students, I want you to check this into the books. We have this book. This is Giancori. Of course, it is a book that some of you may not have at home, but whenever you go back to school, you will now check this lesson into the book. This is page 237 up to 239, and you go to page 251 for some exercises, examples, of course. So, students, the objective of this lesson, I want you to be able to define what is deformation. Deformation. And number 2, I want you to be able to distinguish the elastic from plastic deformation. Will you be able to distinguish this? I hope that you will be able to do. So, and another is to calculate the strain of material. What is a strain? And then what is a strain of material, just from the calculation. And another is to give the quick description that shows stress and the strain curve of a material. Of course, we can't talk about only stress and then forget the stress, yet they talk about, or all of this talk about the application of force on the solid materials. Okay, so this is the solid. So then, students, let's move to the floor here. So we have to define the deformation. According to you, what do you think as a deformation? What is the deformation? Students, I want you to look here. So here I have the 2 bottles. One is this one, but what I can tell you is that this bottle was the same as to this one, was the same as to this one. Do you understand? It means that the bottle here that I have, you see the shape have changed. You see that? So I want you to observe this bottle carefully. And then after you observe the one that I had before, which one is changed? I mean, which one has a shape or a volume or the size has been changed. I feel that you can pick up this one. Let's remove this cover, and then you say which one. Okay, now students, we have the application of force on this bottle so that it has the shape of this one. In another word, deformation is appearing when the application of force is on this material. And then we define that deformation. Okay, students, what we are saying here is that force may produce a change in size and shape of the body. And this time we say there is a deformation. Deformation occurs when the force applied on the material, on the body, changes the size, the shape of that body or that material. And another thing that I can show you, we have the spring mass system here. This is a spring. It is a spring. So let me remove this mass. And you see the spring has the same shape as to that one. But if I apply the force, this time now I'm saying I'm applying the force even if I have the mass, but the mass here is exerting there is a force exerted on this spring through this mass that I'm hanging on the spring here. And then what I have, again, it has changed. You see the length is not the same as to this one. There is a change of length. Now, my dear students, sometimes you can have a material changing up to this level. You see, I can have this spring coming back at the normal size. Do you understand? But if I remove this, I can have that spring coming back to the normal size, to the normal shape, to the original shape. But this time it is not working out for this spring here. Unless if I push. But you see, I'm pushing it, but that is work out to make it at the original shape, original size. And you are going now to understand what has happened. It means that there is a permanent deformation. Do you understand that? Because this bottle here, there has been a permanent deformation. Because if I push this one and then I release, I don't see that it change. I don't see that permanent. But when I press, I apply this force, I apply the load here, and then it is changed. But when I release, it means that the force is released. Then I have the same shape. There is no problem. The same as to what you have here. Then, my dear students, there are the things that you have to distinguish, that you have to just to explain as what is happening to this demonstration that I came to show you there. And this is going to be one. One is here. What I have is elastic deformation. Then, students, what do you think as elastic deformation? Elastic deformation. What is this? Huh? So, elastic deformation, according to what you see, and according to what I want you to understand, it is when I have applied this, and then I have released it, I have removed that load, that force, it came back to this shape, to this normal, to this original size or shape. It is when I have removed this mass, and then it came back to the original shape. Do you understand that? Yes, thumbs up if you understand this. That's good. This is what we have there. And I think that from this diagram, we have a spring, and then we are stretching it, but it is coming back to the normal size. And what is here, again, it is in the same way. Force is applied on this material, and then this is elastically deformed. And here there is back to original shape, original size. Then, students, what is the elastic deformation? Can you define that? Wonderful. A definition is going to be very simple. This is the deformation by which, when you release, when you remove the force, the load on this material, from the material, you are removing the load from the material, and the material restored to the original size, original shape. Do you understand? So here we have a definition. My boy there is answering this, and you are also my students, I know. The object returns to its original shape. Here, the original shape, when the load has been removed. An example, a spring being stretched under normal usage. You see, it is coming back to the original shape. Then number two, we have to explain what is plastic deformation. Then the plastic is going to be this one. Here, even if you try to restore this by applying another force, this will require much more energy for you to restore it to the normal shape. And this is the plastic deformation. It is a permanent now. And you see what has happened to the spring here? The same, permanent. Then, students, what is plastic deformation? This is very simple. This is very simple because this is when You remove the load from this material, but that object is not restoring to the original shape, original volume, original size. It is remaining. Here is what I have said. The object does not return to its original shape when the load has been removed. An example is a spring that has been stretched too far. Then, students, let me advise you on how we have to keep our materials, like these springs, our apparatus, properly. You get that? We have to keep them properly because this spring cannot be used by your next other students. Of course, you are the next student, but you will not use this one because it has been deformed permanently. And what you have to do, sometimes the student, when it gets into laboratory, they stretch the spring and stretch up to the size of their arms. This is not possible. This cannot work out. Or sometimes they can now wear it now around there, of course, as if it is a belt that they have. Don't do this. Do you understand? Because you are changing the springs, you will make the other students not have the apparatus to use in the laboratory. So, but lucky enough, I have used it to demonstrate what is about this permanent, so that you cannot do this mistake again. So this is a diagram that I want you to see. Here we have the two things. It is a mass, it is a load that is exerted on this surface, and here it is changed. When the mass is removed, something now restored to the original, to the normal shape. But this time here, we have a mass, but it is no longer coming back to the normal shape, but it is remaining. This is plastic deformation, and here we have it as that's good, as okay, this is what I have said here. Good, the elastic deformation. Then, students, you know, here we have the application of what we are discussing here. If you have understood what I have said, so this is applied in the construction of various structures like bridges, column, pillars, and so on. Knowledge of the strength of the material used in the construction is of great importance. Because you are going to construct this bridge, and you have to know the materials that you are going to use, so that when the cars with a heavy load passing on this bridge will not deform that bridge. Do you understand? The same as to the house or building, this tall building construction also. You have to make sure the material you are using, they are all studied carefully to make sure that people will step on this, the floor, maybe from number one, but not able to deform that floor. Do you get that point? So you understand now where we have the application of this. So, but you, I think you are the future engineers. You will not make this mistake. You will construct the load carefully. Do you get that? So, and for the cars, a car that is pulling another car, of course, they have to ensure that the loop, the wire, the solid material that is used to pull that another car is properly or is well studied so that it cannot break when the car is pulling another one. Okay, now students, we have to explain what is really a strain. And this is the definition. It's defined as the extension per unit original length. This is the strain. Strain here, strain is defined as this is the formula. Let's say we have, this is the strain equals to E over L0, where, so you say where E is the extension And this L0 is the original length. Okay, I know that you are following me, yes? That's good. So then, students, if we have this, and I think that you see here, this is into meter or centimeters, and this one the same, and you will find this without unit. No unit for this strain that we are calculating. Okay? Now, students, we have another concept. We can't define a stress without strain definition. Strain, I mean without stress. Stress is defined as the force that is exerted per unit sectional area. So this is a definition. In another word, you can understand this stress as which is equal to force over area. And in another word, here unit will be Newton meter power negative 2, or this is Pascal. You can express this into Pascal, right? So this is what we call stress. Now, students, I hope you understand what we are saying here. So I want you to be able at least to define this. So this, as I have said, the title here, we have a strain. But as I'm saying, we can't define this as strain and then forget a stress definition, because they have to go hand in hand. And this time here, we find the ratio between stress and this is and strain, and strain is called elastic modulus. And this elastic modulus is this one, and then you find that is equal to F over A, then over A over L0. And this is going to be again into Newton meter power minus negative 2 or Pascal. This is another concept or another thing that we can define over there. Then, students, let's very quickly have an example. This is an example that I have for you. A marble column of cross-sectional area, 1.2 meters square, supports a mass of 25,000 kilograms. Elastic modulus of marble is E equals to 50 times 10 power 9 Newton per meter square. What is the stress within the column? Students, that is A. Then B, what is the strain? Now, my dear students, I think that we can correct the question there. But first of all, I want you to identify the data. What do we have? Number one, we have the area. The area is 1.2, and that is meter square. And another, what we have there is the mass. The mass is 25,000 kilograms. So which means that from the mass we can find what? We can find the weight, the force. Do you hear that? That's good. And then another that we have there is E, which is equal to 50 times 10 power 9 Newton per meter square. Okay. So then what is being asked is to find A, what is the stress and what is the strain? So stress, strain, B here, strain. What are we going to do? We are going to apply the formula. So now here, if we want to apply the formula, you see what we have said. The strain is here and then the stress. So going to find the stress. Stress equals to, this is stress, equals to F over area. In other words, the force is what I have said to be this is the weight of the material over area. And then let's substitute. If we substitute, you see what we are going to use. 25,000, yes, times the weight. Let's use here, let's use the, this is going to be 9.8 meters square over this area, 1.2 meters square. The unit is going to be into Newton per meter square. That's good. Now what we have is this one. We can calculate and use your calculator, and then you find the answer. So here we have a 25,000 times 9.8, and this is divided by 1.2, and this is equal to, the answer here is equal to, let me use this side. The answer equals 2.04 times 10 power 5 Newton per meter square. And then B is going to be strain. What is going to be strain here? Strain, remember, it is this E, epsilon, E. And this is going to be equal to, you know, we say that is equal to E over L0. Or this E, according to what you have there, do you see that? This E is going to be equal to, that is sigma over E. Why sigma here? Because what I have from this formula is like having E, which is equal to sigma over epsilon. Then you have, that is, here it is the stress over strain. And let's substitute the data here. So then E here equals to, sigma is what we determined to be equals to what? This is 2.04 times 10 power 5 Newton per meter square over, we divided by strain, elastic modulus. That is 50 times 10 power 9 Newton per meter square again. Answer is going to be, let's do it quickly. And what are we going to find? So here we have, this is a 2.04, and then this is divided by 50, and this is equal to, this is 0.0408, then times, you see that when this one goes up there, it becomes 10 power to negative 4. And you know it is without a unit. This is no unit that we have. Then students, I think that you have also obtained the same answer to what I have obtained, but there we have an answer, but of course we are using it 10 power to negative 6, because what we have used here as the calculation, so leading to the same. So you see here we have E equals to 4.08, then times 10 power to negative 4, negative 6, because we are taking it to these two other figures. Students, let's talk about now what we are saying as a really strain. Stress and strain are properties linked to a material rather than to a specific sample of the material. So it means that is for properties linked to material rather than to a specific sample of the material. And the graph that we are having below here should be the same. So the same for any thickness and length of wire made of the same material. So it doesn't change for that material. So this is the graph. Very quickly, I want you to write down this graph. And then I get to explain the graph there. Okay, now good. So with this graph, I think that you see we have the stress here, and we have the strain. From this point 0 up to the point somewhere that we call the elastic limit, this is E, of course. So there we have the elastic region. And from this other point, And we continue, we have the plastic region. It means that is the permanent deformation. Now, students, what you have to understand, so I'm going now to give you this, the brief description of this diagram. The first one thing that I want you to know or to understand is what does this point here shows or means? And then the other next lesson, we should go deep to explain what are these points or what means to this point here. So the point that we have here as a P is the limit of proportionality. That is the limit of proportionality. We'll be saying that for this point, the Hooke's law is obeyed. And you know what is Hooke's law. We will go back, we will again go back to this diagram into the next other lesson. And here we have E represent the elastic limit. And as you understand, if it is elastic limit, it means that if you exceed to that one, something is no longer elastic region or is no longer coming back to the original size, but it is becoming a permanent. It is deformed permanently. So then we enter through the plastic region. So this is why is the yield point. Yield point is there. So then, students, what we have here is this is what we call the ultimate tensile stress. And the last one is what we call the breaking point. From this point, the material breaks. It is broken into parts. It means that if I apply the force on this metal ruler, I continue, but I'm not going to continue because I can break it. I can get to that point of B. Do you understand? And I can't do that because, you know, we have to keep these materials properly for the other next students. Now we have, we can now let's say that after the elastic limit, the extension of the wire is in the plastic region and the permanent deformation is taking place. Then, my dear students, I can't live without a homework for you. This is a homework. I want you to read it and then do it. Stay safe until we meet the next time. And I hope we are going to do more other exercises from books and the internet. Thank you for having me. Bye.